This is our fourth lecture on two separate topics. One of them is the subspace topology, and the other one are bases for a topology. So we have two unrelated topics in a single lecture because the plan is that both of these topics should not take that much amount of time, and we can put both of them into a single lecture. So let's talk about subspace topology. The idea is essentially this. We're going to start, so let x comma t be a topological space. So what this means, to quickly recall everything, x is a set. This is just a set. And t, or script t, is a collection of subsets of x, which you call the open sets, and they satisfy certain properties. So t contains the empty set, t contains the entire set. If two sets are in T, then their intersection is also in T. And if you have a collection of sets in T, their union is also in T. So these are just very quickly to recall the properties of a topology. So this T is a topology on X. And we usually are lazy and we just write X. So often mathematicians will just write, let X be a topological space. They will not even reference the topology, and we just understand that there's a topology on that set that we're not explicitly writing out. We're just keeping it in mind. So this is the setup that we have here. And what we would like to do is we're going to pick any subset A. This is a subset of X. And this is not necessarily open, nor closed. So to quickly recall, open just means that it's an element of the topology. That's what open means. And closed means the complement. The complement is in the topology. And we've made this comment that just because you pick a subset of X does not mean it has to be open or closed. These are not opposite concepts, and it could be also open and closed at the same time. So you pick any subset of X, and what we would like to do is we would like to put a topology on A. So at present, we have a topology on X, and maybe just to decorate it, maybe we'll write over here Tx, T subscript X. Sort of just reinforce the fact that this is the topology on X. So this is a topology on X, and we would like to put a topology on A. So that means we want to create. So we create a new topological space, which we're going to call A comma T subscript. Let's call it T subscript A, because now we have a topology on A. We have a different topology, but this time we're putting it on the subset. And so the reasonable thing to do, so it is reasonable to use the original topology on X, so this is original topology on X, and create a new topology on A. You can, of course, do something very silly. You can put, you can always do this. What you can always do is you can always put the discrete or indiscrete topology on A. But that's kind of silly because A is a subset of X. So you would like to somehow relate this to this. For instance, let's say that X had the discrete topology. So the discrete topology is where everything is open. So you had the discrete topology, and then you pick an arbitrary subset of A. So you pick the subset of A. Now you're going to put a topology on that subset. Now, it would make sense that whatever topology you put on that subset should also probably be the discrete topology, because this larger space that contains it has the discrete topology. But if you really wanted to, you can put on that subset the indiscrete topology where nothing is open other than the two extreme examples. So, and in that way, you can put totally two different topologies that have no relation to one another. But that's not what we want to do. Like if A is a subset, it's coming from X, then it's reasonable that whatever topology we're going to be put on it is going to be in some sense inherited from the original topology. So that's what we would like to do. So I'm going to show you the first approach, the first method that's a little bit problematic. So this you can say is maybe the first attempt. So this is the first attempt. Let's say this is our first attempt. To put a topology on A. So to put up topology on A just means, so what does it mean to put a topology on something? It means to define your open sets. That's what a topology is. A topology is a collection of sets which you call the open sets. So to put a topology on something means to create a collection of sets that will play the role of your open sets. So how does one put a topology on A? So here is a reasonable first guess. So say that U is a subset of A, and since A is a subset of X, right? We are assuming that A is some smaller subset of X. Since A is a subset of X, it means that U is also a subset of X. Right? So if you pick a subset of A, and A is a subset of X, then it means whatever that U is, it will be a subset of X. And so you can try, so the first reasonable choice, the first reasonable attempt to, let's turn this into a verb, to topologize. So to topologize means to put a topology on something. So the first reasonable attempt to topologize A is to say that a subset of A is open if and only if U as a subset of X is open. Because we already have a topology in X. So you say a subset of A is open. As a subset of A, it's going to be an open set. When you view it as a subset of X, it's going to be open. And that is somehow the reasonable way to do it, but there's a problem. So here's where the problem is. So the problem with this approach is that A is a subset of A. So A needs to be open as a subset of A, because that's the requirement for a topology. Whenever you put a topology on a set, the entire set itself needs to be open. So if you this A has to be an open subset of A. But the problem is, however, A as a subset of X is not necessarily an open subset of X. Right? When we pick this, in the beginning we've said that you have a topological space and you pick any subset of X and you want to put a topology, you want to topologize this A. Now, if this A happens to be an open subset, then the approach that we just written out, it makes sense. You can do that, right? You can then say that the open subsets of A are exactly the open subsets of X that are contained in A. Because for what will happen is, if A itself is already open, then A is a subset of itself, but it's also an open subset of X, and so A would therefore be open as a subset of A. However, A is not necessarily open, so this approach does not quite work out. So we have to do something that's a little bit different. So here's the way we're going to do it. So let's remove this, and let's make this a definition. So let X comma Tx be a topological space, and A is an arbitrary subset, of X, the subspace topology let's call it TA. The subspace topology of A is defined as follows. So you say that U is in the topology, so this is the topology of A. So this is another way of saying, this is just another way of saying open in A. Okay, all that means is that U, that's going to be a subset of A, because the topology on A is a collection of subsets of A. So whatever this U is open in A. So you're defining what it means to be an open set. So U is an open subset of A if and only if and only if. So it's a little bit similar to what we said before, but it does not exactly work because A is not necessarily open itself. So if and only if U can be written in the form V intersect A, where V is in the topology of X. So this is another way of saying open in X. So we're basically saying that open in A, so an open subset in A looks like this. It's an open subset in X. It's an open subset in the larger space, but then you intersect it with A to bring it back down to A because it has to be a subset of A. So that's basically what you do. And this is called the subspace topology. And it's an exercise, let's write this as a proposition, that A comma TA, well, actually, let me write it like this. TA is a topology on A. And this is going to be an exercise. You can try doing this yourself. You can, of course, find it in Moncrief's, but it's fairly straightforward enough. So now we're going to look at an example. I do want to make a small comment here, and that's what happens if A happens to be open itself. So this kind of goes back to what we were saying at the very beginning of the lecture. We were saying that a reasonable way to define an open subset of A is to just say it's an open subset of X that just happens to sit in A. But we have to do something like this because A itself is not necessarily an open set. So therefore, let me say this. I'm going to take this down, and let me write down this proposition. Let X comma Tx be a topological space, and A is an open subset of X, and which just means that A belongs to the topology of X. Then the subspace topology of A is contained in the subspace topology of X. This is just another way of saying. So if U is in TA, then U is in Tx, which is and another way of saying that is you can just reformulate that. You're just saying if U is open in A, so if U is an open subset of A, then U is open in X. That's what you're saying. Instead of writing this, we just say U is open in A. And instead of writing that, we rather just say U is open in X. It's an open subset of X. So this might look complicated, but it may be in simpler language you're saying that an open subset of A is an open subset of X. So this is actually the way we wanted to do it in the beginning, and this works if A itself is an open subset of X. If it's not an open subset of X, then the then this topology will not be then this topology is not contained in that topology. It's a slightly different topology, but it's still very similar to the original topology of this larger space. So let's give a proof of this. This is actually, fortunately, very easy. So proof. So let U be a subset of A, be an open set. And there's no ambiguity. If I just wrote let U be an open set, that's confusing. But when I'm writing let U subset A be an open set, it's understood that U viewed as a subset of A is an open set, which is another way of saying U belongs to this. So let U be an open subset of A, then by definition of the subspace topology. So this just goes back to the definition of how the subspace topology was created. This means that U is equal to V intersect A, where V is a subset of X, is an open set. Because what's the subspace topology? The subspace topology, to put it very simply, it says open in A has the form that it's open in X, and then it's intersected with A. That's the definition of the subspace topology. The open sets in A, they have the form that they come from open sets in X, but they're being intersected with A. So this means that U has the form that it's V intersect A, where V is an open set. So V as a subset of X is an open set. But V is open in X, and A is open in X. So why is that? Well, that's what we're assuming, right? V is open in X. That's just a part of the subspace topology. And A is open in X because we're making the special assumption that the subspace that the subset that we chose in the beginning was an open subset of X. And A is open. So V and A are open subsets of X. Therefore, V intersect A is an open subset of X. Because that's the finite intersection property, right? This is the finite intersection of open sets. So if you have two open sets, then their intersection is an open set. So V intersect A is therefore an open subset of X. But what is V intersect A? V intersect A is U. So this is just another way of saying U. So U is an open subset of X. So basically, this is exactly what we said. If U is an open subset of A, then it's also an open subset of X. Okay, that's what we said. As you can see, this stuff is very easy, actually. There's just a lot of definitions. And this is exactly why we call this. So maybe you're beginning to understand why people in the math community call this point set topology. You're not doing anything super exciting. Like you're working like almost entirely containing sets, and then you talk about elements coming in sets, and then a lot of the arguments, they involve subsets and intersections and unions and things like that. So it just is beginning to feel like one of those early proofwriting classes that you take. So everything is just manipulating these kinds of set operations to make things work out and just recalling the definitions. And whether or not you find it interesting or not interesting, I think it's interesting up to a certain point. I think it's interesting in the sense that it's nice to see how a lot of these intuitive notions about shapes can be nicely summarized as various set operations, and that's nice to see. So you're like able to formalize the things that you want to say. But so I think it's interesting in that sense, and it also shows that you're doing rigorous mathematics in the end. But one can very easily overdo it. You can just start talking about very bizarre kind of spaces. We actually contained ourselves last time. Last time we saw there's a lot of different separation properties, and you can just go way off topic and start talking about all of the different ways you can separate points in the space. So if you recall, we had T2 separation, T2.5 separation, T3.5 separation, T6 separation, and so forth. And then asking what kind of a space you have, and we've decided not to go there because that is actually not as important in general mathematics. So so I want to show you an example. So let's work with an example. So here's an example. So let's work in R2. So let R2 have the usual topology. Now, you can put any topology you want on a set. So if you wanted to, you can put the discrete topology on R2 where everything is open. You can also put the indiscrete topology, but usually in 100% of cases, whenever you see R2 or R to the n, anytime you see Euclidean space, what we refer to the usual topology is the Euclidean topology. In other words, there's a norm. This is why we talked about in the first lecture. There's a norm on Euclidean space. It does not matter what norm you pick, and then you use that norm. That norm gives you a metric. It gives you a way of measuring distances. And once you have a metric, you have a topology out of that. So the topology is what we call the usual topology on Rn. So whenever you write R2 or Rn in mathematics and you do not say anything else, if you treat it as a topological space, it's always understood that it's the Euclidean topology that is being put on it. Unless you're doing something out of the ordinary, and then you have to explicitly tell the reader that you're doing something out of the ordinary. So this is R2 with the usual topology. And now let's pick a subset, and we're going to specifically pick something that is not an open subset. So and A is going to be the following closed square. So if you're not familiar with this notation, if you've never seen this notation, this is the interval from 0 to 1. This is a Cartesian product. So you're saying the first coordinate goes from 0 to 1, and the second coordinate goes from 0 to 1. So the way this is going to look like is you're going to have a square like this. You're going to have this closed square. So this A is closed subset of R2. We're not going to prove it's a closed subset. You can try to think it through why that is more carefully. And A is not an open subset of R2. A is not an open subset of R2. It's not enough to say that just because A is a closed subset that it's not an open subset. Maybe it could be both. But the fact that it's not an open subset, that should be clear, because the definition of an open subset is if you pick a point, let's say you pick this corner point, can you fit a disk centered at that corner point? Well, you can see that no matter how small you try to draw that disk, no matter how small you make that radius, you can never make it completely fit inside this set A. So A is therefore not a closed set. And by the way, maybe you recall we've talked about this. The interior of A, if you're wondering, this is not really surprising, it would be this open interval times the open interval. So it would be exactly this, but not this 4 edges around it. That would be the interior of the set. Okay, and let us draw some pictures. Draw some pictures of open subsets of A. Open subsets of A. So here we're working with the subspace topology. Okay, so basically what we're doing is we're going to think of A as a topological space with the subspace topology. So maybe to make nicer pictures, I'm going to redraw this again, just a little bit bigger and without the extra lines. So this is A right here. And the subspace topology goes like this. Open in A has the form that it's open in X. In this case, X is R2. And then you intersect it with A. So take any open subset of R2 and intersect it with A and see what you get. So let's say you take this open disk. So here's an open disk. If you take this open disk and you intersect it with A, you get this open disk. So this open disk that you see over here, that's an open subset of A. So this open disk is both an open subset of A and it's an open subset of R2. However, imagine that you take an open disk and you draw it like this. That's your open disk. So when you intersect it with A, you actually pick up this edge. You pick up this edge and then you pick up that side, but not counting the boundary, and you get this. And then you would remove these lines because they're not part of because they're not contained in A. And you get something that looks like this. So this is an open subset of A. You see, it's interesting that you have like this open edges going around, like what you would expect. But then this entire edge is solid and it's included, and yet this is an open subset of A. This is not what you would immediately think at first, because this is not an open subset of R2, but this is an open subset of A. And then you could also do the same thing with the corner. So if you were to draw, let's say, an open disk right at that corner, and you intersect it with A, you're going to pick up the part that intersects it with A. So you're going to pick this up, you're going to pick that up, and you're going to pick up all of this. And then you would remove the part which is not actually part of, which is outside of A, and this is an open subset. So this is also an open subset. This is an open subset of A. This is not an open subset of R2. So let's just indicate this. So this and this, these are open subsets of A, but not open in R2. And this one, in this example, this is an open subset of both A and R2. So you could have an open subset that is an open subset of both A and the larger ambient space, but then you also have cases like this that would look a little bit different, okay? Now, if A itself was an open set, so let's go back to this example, and let's say that A was not this. Let's say this was A. Let's say A was the open, let's say that A was the open square. Well, if A was the open square, then these edges would actually be open, right? These edges would not be part of your space. So these edges would be open. So you have to therefore somehow change the picture a little bit so that so this will actually look like this, right? Because these solid edges, they're not supposed to be included if they're not included in A. And the same situation would be over here. This one would look like this. You're not going to be including that bottom edge. And then if A was open itself, then this would be open in A and open in R2. And this one would be open in A and open in R2. So then actually everything that is open in A would be open in R2. But that makes sense because that's what we were saying, that if A itself is an open set, then the open subsets of A are precisely the open subsets of R2 that just happen to be contained in A. So that's what that earlier proposition said. Okay, so let's take this down. This is a fairly simple example, but I think it's very helpful. Now let's make this proposition somewhat interesting proposition. So here's our proposition. So let X be a topological space. And I want to deliberately be very sloppy over here and not write Tx, because this is the way it's usually written in mathematics. So we have this topological space, and A is a subset of X with the subspace topology, which is what happens all the time. In topology, if you pick a subset, you always put on it the subspace topology, because that's the reasonable thing to do. The topology of a subset should resemble the topology of the larger space. If the author never says what kind of topology it has, it's always understood to be the subspace topology, unless you're doing something really strange, and then you will have to deliberately tell the reader that you're using some kind of different topology. that you've never mentioned. So X, we have a topological space. A is a subset of X. We're not assuming it's open or anything like that. A is a subset of X, and you're going to give it the subspace topology. So X and A, they're both topological spaces. And this is the proposition. So let's say C is a closed subset of A. So a subset of A is closed if and only if C can be written in the form K intersect A, where K is a closed subset of X. So basically what we're saying is closed in A has the form that it's closed in X, and then you intersect with A. So it's very similar. The difference is, like, why is this a proposition? Well, because the one with open in A is open in X intersect A. That's the definition of the subspace topology. But what happens with closed sets is now a consequence of that definition. So this is what we're going to prove. And as you can see, if and only if statement. So we're going to be lazy, as we always are. We're only going to prove it one way. I'll prove it to you in this direction, and then you can prove it in the other direction. So we're going to prove that if you have a closed subset of A, then you can always write it as, you can always find a closed set in X, so that when you intersect it with A, it returns you back to C. So let's write out the proof. And all of these are generally very easy. And let me, while we talk about easy proofs and hard proofs, this is sort of like the definition between, this is sort of like the difference between a proposition versus a theorem. Like, what's the difference between these two? Proposition is a fact which is generally very easy to prove. It's usually just playing around with the definitions and moving them around, doing what you think you're supposed to be doing, and then everything works out. And a theorem is usually something that's very difficult to prove. There's a lot of steps, a lot of ideas. There's something clever going on. Maybe it's very long. Sometimes propositions are very long to prove, but there's nothing surprising. It's like every step is exactly what you would think it is. So anytime you see a proposition in a math book or in a paper or anything like that, that generally tells you that it's something you can prove yourself if you just carefully follow the definitions. When you see theorem, then you want to be a little bit more concerned. Maybe that's actually difficult to prove. Sometimes certain theorems in mathematics are fairly easy to prove. They're not necessarily hard, but they're very deep and they mean a lot. So there's sometimes situations where something might not necessarily be difficult to prove, but it is very valuable and it's used everywhere. But here, proposition all it's telling you is that there's nothing clever. You can prove this yourself. In fact, if you wanted to, you can pause the video, see if you can do it yourself. We're only going to prove it in this direction, and then on the homework, you can do it in the other direction. So here's proof. Let C be a closed subset of A. Therefore, if you take the complement, A take away C, that's the complement. So A, and then you take away C, and then whatever you're left with, that's the complement. It is an open subset of A. By definition, that's the definition of a closed subset. It means the complement is going to be open. We're taking the complement in A because C has a closed subset of A, so it's the complement in A. So from A, we take away C, and whatever we're left with, that's going to be a subset of A. So that's going to be an open subset of A. So therefore, thus, A take away C, because it's open by the subspace topology, there is a V, so that you can write in the form V intersect X, where V is open in X. This is just a definition of the subspace topology. Something is an open subset of A if it can be written. Oh, I made a mistake here. I wrote V intersect A. I meant to say V intersect. I wrote V intersect X. I meant to say V intersect A. That's what I meant. So the open subsets of A, they have the form that it's something that's open in X, and then you intersect it with A to get a subset of A. So you have that. And now we go backwards. Now we take the complement again. So then take the complement. So let's do this. Let's do A, and then we take the complement of both sides like this. There's different ways you can do it. This is the way I'm going to do it. You might have your own way of doing it. And so you're just taking the complement of both sides. Like this. Okay, so you see this is here, and this is here, and then you have complement. So A, take away this. A, take away this. These are equal, so you're just taking complements. Now this, that's just C. Right, that's just C. This is everything in A that's not in C, and then you're saying, well, what is not in A, but in C? So that's just C, right? So that's just the double complement returns you back to the original set. Now this next one, I think it's helpful to draw a picture. I think the picture here will help you see what's going on. A Venn diagram. Let's draw a Venn diagram. So the square represents X. That's like your ambient total space. And then you have a subset. Let's say this triangle that represents A. Right? So this triangle represents A. And then you have V. So you have A and you have V. V is something that's open in X. So let's draw a circle. So that's V. So when we do V intersect A, V intersect A, we're getting the intersection between A and V, but we want the complement in A. So when you shade this in the picture, this is what you end up getting. So that's the part that's being shaded in. So V intersect A, that's where these two overlap, and it's the complement in A. From A, you take away where they overlap. Now you should be able to see from this picture that this can be rewritten. This can be rewritten in the following way. You can rewrite this as A intersect the complement of V. So you can rewrite this as X take away V. So let's just see why this works in the picture. The complement of V in X, so this is the complement in the square. So from X you take away V, so you're getting all of the piece, you see, you're getting everything outside of V in X. Getting all of this stuff outside. So we're just to shade this in, this is what we're getting. This is the complement of V. See that? That's the complement. This is the complement of V in X. That's what that is. But you want that piece of it, but if you intersect it with A, then you're getting that blue piece, which is exactly what you have over here. Now, this is a pictorial proof that you can rewrite this into that. If you want to write a more rigorous proof, you have to do like one of those set theory arguments. You pick an element over here, and then you show it's an element over there. And then you pick an element over here, and you show it's an element over there. But that's not very exciting. The main idea is you can rewrite this complement in this kind of a way. And now, what do we see? This, we can call that K. And this is a closed set. A closed set in X. Why is that a closed set? Because V, you see this V that we had over there? V is an open set in X. So its complement in X, by definition, is a closed subset of X. And look at what you have. A closed subset of A can always be written in the form as a closed set in X intersected with A. Okay, that's what we're saying. If you have a closed subset of A, it can be written in the form that it's something that's closed in A. It can be written as something that's closed in X, closed in the larger space, but intersected with A. So that's what we've proven. And now you can go in the opposite direction and show that if a set can be written like this, then it's necessarily a closed subset of A, which not very difficult. So you can do this yourself. We'll put that on the next list of homework problems. So now the next thing that I wanted to mention, maybe we can even make this comment. So this is an immediate consequence. This is sort of like a corollary of what we've just said. So if C is closed in A and A is closed in X, then C is also closed in X. We've actually already proven this with open sets. If you recall, we said that if something is an open subset of A and A is an open subset of X, then whatever that set was, it's also an open subset of X. We've actually proven something like that before with open sets. But now we have the same situation with closed sets, and it just follows exactly from what we just said. If C is closed in A, so here's the proof of this. If C is closed in A, then that means C can be written as K intersect A, where K, this is where this one is going to be closed in X, and this is closed in X. So here we're assuming that A is closed in X. But then look what happens. This is closed subset of X. That's a closed subset of X. And the intersection of two closed subsets of X, when you take the intersection, this is a closed subset of X. And so it follows that this C also has to be a closed subset of X. So that's the way that it works. It's a very simple consequence of what we've said. Okay, so let's say one more thing. Let's say something about closure. Let us say something about closure with respect to a subspace. So if you recall, from last time, we introduced this operation in topology called closure. So recall, so X is a topological space, and A is a subset. So we define this thing called closure. So this is called the closure of A. So the closure of A, by definition, this is, so it's called closure because of closed. This is the smallest closed set containing A. If you want to write it out, what that means is, here's the way you do it. You're going to take the intersection, because you want to try to make it as small as possible. You're going to take the intersection of C, where C contains A and C is closed. This is closed in X, of course. So that's the definition of closure. There are different ways to define it. As I said, if you open up Moncrief's or any other book, you might see it defined differently. But whatever definition they're using, it's going to be equivalent to this one. So they're not really saying anything new. It just looks different. And what we want to say, we want to mention this property of closures that goes like this. So let's write a proposition. So let A be a subset, of X with the subspace topology. And usually we do not even say that. It's understood that it has the subspace topology. And pick any subset, let's call it B, of A. Right? So B is a subset of A. Not necessarily an open set or anything like that. So you might ask, you can take the closure of B. Let's write it like this. This is the closure of B in A and the closure of B in X. So that's the way I'm going to write it. So this is the closure of B as a subset of A, because B is a subset of A and A itself is a topological space. And this will be the closure of B as a subset of X. So what can we say about this? Are these the same? They will typically not be the same. If you take the closure of B and A, the largest this can possibly be is A. But if you take the closure, because you probably recall we had this example so let me make a comment. You can pick, we had this example last time where X was the set of real numbers and A was the set of rational numbers. So X was the real numbers, this were the rational numbers, and we saw that the closure is actually everything. So A is a subset of X, but it could happen that its closure is actually everything. So if you pick a subset of B and you take the closure of it as a subset of A, the largest this can be is A, whereas the largest this can be is X. So clearly these are not going to be equal to each other in general, but the reasonable thing to do is maybe you're supposed to intersect it. This is probably what you would guess, that if you intersect it with A, then maybe these become the same. So that's what we're saying. That if you take the closure of B as a subset of A, that would be the same thing as taking the closure of B as a subset of X and then intersecting whatever you get with A. So that's the way this would go. So this is the proposition. And yeah, so it's a proposition. It's not very exciting to prove. This is just more stuff with sets that one has to do. So let's discuss a proof of this, why these are equal. So here's the way you can do this. You can proof. So B closure X is a closed subset. It's a closed subset of X. By definition, right? Because the closure in X, it's the smallest closed set that contains B. So this is a closed subset of X, and it contains B. Therefore, B X is, so therefore B, the closure of B and X intersected with A is a closed subset of A, and it contains B. Why is that? Well, this is the earlier proposition that this entire thing, whatever that is, that's a closed subset of X. So if you take a closed subset of X and you intersect it with A, our earlier proposition says whatever you're left with is a closed subset of A. But furthermore, we know that B itself is contained in A, right? This thing contains B, and A contains B, so this intersection contains B. So this is a closed subset of A, and it contains B. So therefore, hence, B closure A is contained in this. Since, why is this? So since the closure of B and A is the smallest closed subset of A, which contains B, right? On the previous line, we said that whatever this is a closed subset of A, and it contains B. But by definition, the closure in A is the smallest closed subset of A, which contains. So since this is the smallest such closed set, whatever this is, it's less than, not less, well, I mean, it's a subset of whatever that is. And I'm going to be lazy. I'm going to be very lazy here. And now you can show, it would be nice if you can do this on the exams, but you can show that it's also true the other way around. I mean, this is really boring stuff. Like, if you're looking at this and you're saying, this is kind of boring, where do we get to the more exciting parts? Like with donuts and spheres and Mobius bands, stuff like that. Where do we get to the more exciting part? So that part is coming. Like, we want to actually get to that part. But we actually need to pain ourselves through all of this boring stuff first. So I'll just leave it. I'll just leave it at that. Let's not go any further. It is described in Moncrief if you really want to see it. Now I would like to switch topics and talk about bases. So there's actually not that much to say about bases. So the idea of a basis, maybe we should say a topological basis. A topological basis is that it is difficult to describe all open sets. It's hard to say how they look like. So, for example, in R2, the open sets can be quite complicated. You can have something like this. You can have something that goes like that, and it has a lot of holes in the middle, right? And then it's all filled in. You can have a lot of holes. That would be an open set. Or maybe you would have something like this, and then it's missing like pieces of arcs. There's like these arcs missing, and then that would be your open set, right? And then like that would be your open set, and then it has like these missing arcs. So it does not even have to be connected. It could be broken apart. So you can have something that maybe goes like this, and then something that goes like this, and then this would be an open set. So that would be another open set. So it's very hard to say how all open sets look like. There's way too many of them. And when you just imagine an open set in general, that's hard to do. But the way we define an open set is we say that whatever an open set is, they all have this property that for every point, you can fit a disk inside it. So you all have that property. And working with disks is very convenient because a disk is something very easy to visualize. So even though all open sets, there's way too many of them, and it's hard to describe all of them, we only focus on the open disks because they're far easier to work with. And that's the idea of a basis, of a topological basis. Instead of talking about every conceivable open set that you can have that can begin to be very complicated, you instead only describe a smaller collection of open sets which are far easier to visualize and work with. And that's the idea of a topological basis. So let's make this definition. So here's a definition. Let X be a set, and then a collection of sets, of subsets of X. And let's call this collection script B for basis. So when we talk about a topology, we call it like script T. So a collection of subsets of X called script T, those are all of the open subsets. But there's going to be a basis that's going to be a smaller collection of sets. So a collection, let's call it script B, of subsets of X is called a basis for a topology when the following properties are satisfied. So the first property is for any point in X, there is something in the basis. So you can find B in script B. Or you can say maybe U in script B. Maybe you should say U. You can find some set in script B so that the point is contained in U. So basically what this is saying is every point is contained in somewhere in some set in the basis. You can find something in the basis that's going to contain every point of X, which should make sense because everything is supposed to be in the basis. Then the next property says that if U and V are in your basis, and P is a point that they share in common, then, now here's the thing. This collection B, you see, we do not call it a topology. We call it a basis for a topology. It itself will not necessarily be a topology because in a topological space, one of the requirements is that if you have two open sets, so if two things belong to your topology, then the intersection of them have to belong to your topology. But this is not going to be a topology. This is going to be something else. This is called the basis for a topology. So instead, it has a slightly different property that if two things belong to your basis, and there's a point that is in common to their intersection, we're not going to necessarily say that that this intersection is back in the basis, because this is not necessarily a topology, but instead that there is a W in the basis with the point in W, and W is smaller than this. So the picture that you want to keep in mind is basically this. If this is like U, and let's say this is, maybe draw a little bit better, and this is V, this is the intersection. We're not necessarily saying that the intersection is part of the basis. Instead, the required property is, if you pick any point in the intersection, you can fit something smaller that contains that point inside the union, and whatever that is back in the basis. So this is the definition for a basis for a topology. And let me give you some examples of how you can do this. So let me give you some examples of this. So hopefully this will clarify this for you. So here's an example. So the example here, that this is like probably the best example you can think of. This is exactly what happens in the metric space. That consider R2. So consider the Euclidean plane, and the basis here. This is going to be the collection of all open disks. This is going to be the collection of all open disks. So the idea is that whenever we talk about open subsets of R2, we're not imagining open sets in general, we're just imagining open disks. So, and the reason why this works is because if you have one open disk, right? Let's say this is an open disk, and then you have another open disk. When they intersect, the intersection is not necessarily an open disk, as you can see. But if you pick a point in the intersection, you can always fit a smaller open disk inside it. So, and it therefore satisfies the property of a basis, because every point in R2 is contained in some open disk. And furthermore, right, so the first property is satisfied, and then the second property is satisfied. That if you take two open disks and you pick a point, if they happen to intersect, and there's a point that is in common to both of them, then you can find something smaller that contains that point and is also in your basis. Alternatively, you can also do this. Alternatively, you can also consider B. So we're going to use a different basis. This is going to be the collection. Maybe we should call it B prime. It's a different basis. This is the collection of all open rectangles. So open rectangles. This one is actually a little bit more interesting for the following reason. Because if you have one open rectangle, so here's like an open rectangle, and then you have another open rectangle, and they happen to intersect, then something interesting happens, that their intersection is another open rectangle. I'm gonna make it solid, but we understand that this is open. It's going to be another open rectangle. So what makes this interesting? So in this example, if U is in B prime and V is in B prime, and if U and V intersect, then their intersection is also in B prime. So if two open rectangles happen to intersect, then their intersection is an open rectangle, so by definition, it's part of B prime. So you have this. You see, it's not a requirement that the intersection has to belong to B, but it could. Like in that example, it could. The only requirement instead is that the intersection, any point in the intersection, will contain something smaller, which is in the basis. But that's what you call a basis for a topology. And so why do we use this? Well, here's the reason why we do this. So we can maybe write this proposition, which I'm not going to prove. It's done in Moncrief if you really want to see it, but it's basically this. So let X be a set and be a basis for a topology. Maybe we could call it a topological basis. Let's just call it a topological basis. Then we can use the basis to topologize X. Because at the moment, X is not necessarily, so we're not saying that X is a topological space. We start with a set, then we form this thing called the basis, and we're going to use the basis to create a topology. So the way you do it is, it's exactly the way you do it in a metric space. So in a metric space, you say that something is open if for every point you can fit a disk. Now, what's special about a disk is that a disk is like a special basis element. So you're going to do something very similar over here. So you will say, so we define a subset of X as open if and only if for any point in U we can find a basis, something in the basis. So let's call it B. So B in script B, so that the point belongs to B and B is a subset of U. This is exactly how it works in the metric space, right? That's exactly how it works in a metric. In a metric space, you say that something is open, you say that U is open, if and only if for any point you can draw a disk that contains the point and the disk entirely fits inside it. So this is basically what you're trying to do in general, but you're not using metrics. You're using something else called a basis, a topological basis. And the reason why this is convenient is because the collection of all open sets, the collection of all sets that are open can be enormous. They can be very, very hard to describe. It's just like that example that we made earlier. Just try to imagine how all of the open subsets of R2 look like. You cannot really imagine it. They're way too complicated. So instead, if you restrict yourself to only open disks, it allows you to investigate an arbitrary open subset of the plane by just thinking of open disks, by sort of reducing everything back down to open disks. And this is often what one does with topological spaces. Instead of necessarily trying to describe all open sets at once, you pick a topological basis and then you use it to create a topology. And then the actual proposition. So when you look at this, you might say, well, what's the proposition? So the proposition is this. The proposition is, so this defines a topology on X. So this definition gives you a topology on X. So if you define an open subset of X as something that satisfies, you see, you're saying that this is open if and only if it satisfies this kind of requirement. So now you have to check that the collection of sets that satisfy this kind of property, they end up forming a topology on X. Okay, and this is a useful way of how you can create topological spaces without the need of listing every single open set. So by using this notion of a topological basis. So it's heavily inspired by what one does with metric spaces. And I want to finish with this. This is maybe an interesting thing to mention, but for R2, again, with the usual topology, it is possible to find a countable topological basis. Topological basis. Countable as in it's a countable set. Countable topological basis. In other words, i.e., that this collection is a countable set. So the collection of all disks is too big. So I'm going to tell you how to do it. So here's the way you do it. So you let the basis consist of the following collection. There's going to be a collection of disks. So we're going to have disks that are centered at P with a certain radius. And we're going to require that whatever the point is, it's a vector in Q2. So it has rational coordinates. Actually, there's nothing special about R2. You can do this in Rn. So it has rational coordinates, and the epsilon, it's positive and rational. It's positive and rational. So then B is a basis for R2, and it is a countable set. The fact that it's a countable set just simply follows from the fact that you're only using rational numbers. The rational numbers are countable. So whatever this point is, the coordinates have to be rational numbers. So the choices for P is countable, and the choices for epsilon is countable because the radius must be chosen to be a rational number. And then this collection of disks would therefore be a countable set, and it will form a basis. Now, the reason why it forms a basis, I think this might make a good homework problem for you to think about and write a more rigorous proof. But the idea here is basically this, that if you have an open set, right? So let's say you have some open set. If you have an open set, you can for any point P, you pick inside it, you can fit a disk. Okay, you go ahead and you fit a disk. But the rational numbers, if this P itself is not a rational number, then you can draw a rational point as close as you want to it. Let's call it Q. Because the rational numbers are dense. They're dense, so you can make it as close as you want. And then you draw a small, and then you can draw a radius of rational radius, of a rational number radius, small enough so that it will fit inside that disk. And then it contains the point. So the point is that if you find a disk that fits inside you, you can modify that disk to have a rational radius and a rational rational radius and a rational center. And so you can therefore exclusively work with a countable collection in a basis. So I think the terminology that we use here is called first countable. So yeah, it's called first. Actually, I'm looking it up right now. There's something called first countable and second countable, just to be, yeah, I think it's called second countable. First countable is something else. So this is like the technical terminology here. So let me just finish with this. So definition X. So this is a topological space. So a topological space X is second countable. So that's like the complicated, fancy terminology. Is second countable if and only if X has a countable basis. It has a countable basis. So what this means is you can find a topological basis whose topology will generate for you the topology on X, and it's a countable basis. So it's called second countable. This is used in some technical arguments in topology. Fortunately for us, we're not going to have to use it in this class. There will be one instance where I can imagine where this is going to come up again, and I just want you to know what that means, so you at least have heard of it and you know what this is. There's also something called first countable, which we're not going to even discuss. We just do not need to know that. So we'll finish with this, and now that we have a good understanding of topological spaces and their subspaces and various topological operations, the next thing we're going to talk about is we'll talk about continuous maps. So we talked about continuous maps before between metric spaces, but now we'll talk about continuous maps between topological spaces.